Hi everyone. Today we're going to look at a topic that is named asymptotic behavior of functions. What does this mean? Whenever you are given an algorithm or a computer program and you are asked to analyze this program as a computer scientist or software software engineer, you got to arrive at a function, something that looks like this. You got to arrive at a function because that function will help you to analyze a lot of things about the program, especially the efficiency of the program, which is mostly what we're interested in. So when you see these ends here, this is just the input. For example, if you are given a mathematical problem, say 2 times 2, this is n, this is your input, this is the input, this is the n. What do you get? You get 4. Quickly you get the answer. If now you are given 2 times 2 times 2, what do you get? You get 8. If this number keeps on increasing, keeps on getting bigger and bigger and bigger, then how long will it take you to get your answer? How long will the computer take for it to produce the answer, to give the output? So that is what you are trying to work out here. When you hear about asymptotic behavior of function, that is when this number gets larger and larger, then you got to assume how the computer is going to behave. It is going to be slow, or is it going to be fast, or is it going to remain the same regardless of the input value. So now we are given this problem here. They say by calculating an appropriate limit or otherwise show that this function here is in big O n raised to the power of 4. That is, you analyze your program, you get something like this. You get this function. They want you to show whether it is in big O n raised to the power of 4. So how do you go about this? This is limit. Now we need n4 because the problem is asking us about n4. And you know, in order to analyze this problem here, we've got to take limits, right? So limit, LIM, we'll abbreviate as n, this n, the input function, as n tends to infinity. This is infinity. So we write the whole equation again. 5n to the power of 8 plus 21n to the power of 5 plus 73n to the power of 2 plus 19. We push this one here, n to the, got to divide it by n4. Because this is what you want, whether this function is in big O n4. So this is what you want. This is what we need, the limit. So now we're going to check this one out. If you have n4, if I make it n4 is here. If I make it n8 and I give you this exponent, I did the same. This one and this one. Yes, because if you just, what you are having here, you are now having n to the 8 according to the laws of indices divided by 2. So 2 can go here 4 times, here is 1, so you still get your n to the 4, right? And you know, this n to the power of 8 all bracket to the power of half can also be written as n to the power of 8. You know this symbol, when it is up, it's just finding the square root, simply finding the square root of n raised to the power of 8. Yeah, so that is the case, which means we can then bring this one here, and then we extend this square root sign. Yeah, so we can now say this is 8, and this square root sign will now come cover the 8. Okay, fine. So now we can easily divide here, divide whatever we are able to divide. We still have our limit. The limit as n tends to infinity, when n keeps getting bigger and bigger, then this number we have here, this n to the power of 8 can cancel this n to the power of 8 as well. So what will remain here, just 5 plus. You have n to the power of 8 divided by n to the power of 5. You have your 21 first. So we are doing indices now here. So this would be n to the power of minus 3. N to the power of 8, we have your 73 here, divided by n to the power of 2. So this one will give us n to the power of minus 6. And plus 19, n to the power of minus 8. This is what you get. Yeah? So what this means, if we write it in a way that is simple to read it, we have the limit as n tends to infinity, 5 plus 21 all over n to the cube. This minus now it goes down, plus 73 all over n to the 6, then plus, did I have 19 here? Yeah, I forgot here, sorry. 19 n to the n to the power of minus 8. Sorry. Yes, 19 all over n to the power of 8. So this is what we got. Yeah? So now, as this number keeps getting bigger and bigger, what will happen here? You have 21. If this is 100, or this is a million, so it's going to approach to 0 here. This is going to approach to 0. This will approach 0. This will approach 0. So what is left? You just have the limit as n tends to infinity, then you have the square root of 5. This is what you get, square root of 5. Then there is a rule. Since this number is positive and finite, this is a number we know is square root of 5. It's a number, it's 2 point something. So since this is positive, it's not negative and finite, the rule says that then this function is in omega, is in big O n to the 4, because this is positive and finite. That's the rule. There are rules you look at. So then this equation then is correct. Let's look at the second problem quickly. Come on. Let's look at the next problem. See what we get. You can follow me on YouTube if you want to watch these videos, the full version of them. You can go to YouTube, my YouTube channel, just type MUNIRRMKTURAY. This is my YouTube channel. Then you can watch all the videos, yeah? You can choose the ones you like, you watch them. But you get the full version of the videos on Facebook, Instagram, and other platforms. You won't get the full version. What I'm saying is, let's look at the next problem quickly. The next problem says let k equals this. Let's f comma z shows that all positive integers are mapped to all positive real numbers with fn f of n equals the lean natural logarithm of n. Normally it's like this, natural logarithm of n, and g of n equals n. So again, they want you to show what? Whether f of n is in big O g of n. Whether f of n is in big O g of n. They want you to show this. Just like the previous one we've done, almost the same way, but they just keep changing the question, but it's the same thing. Yeah, if this was a function, we are given like an equation, like what we have done. They gave us one equation, yeah, and they ask us, they gave us two equations. Here is not equation now, they give us this kind of way, functions this kind of way. So now we have here, let's f comma g is shortcut. This is how we read them. Positive integers are mapped to positive real numbers with f of n equals the ln of n, natural logarithm of n, and g of n equals n. That's the question. F of n. Correct. So again, we take limits. The limits as n tends to infinity, the ln of n over n. This is the function. So here, there are so many methods of solving problems involving limits. This limit is a very important topic in mathematics. In fact, this is what makes this branch of mathematics that is called calculus. It's limit that makes it possible. Without limits, this idea of limits, there is no calculus. And without calculus, we cannot send robots to the moon. So this idea of limits is a very important topic. When you start to do calculus, you start with limits. That is your first topic, and it's difficult, short. We shall cover it in a later time. So now, when you look at this problem here, you are taking the limit of the natural logarithm of n over n. It's easy for you to see that if you take the limit of n, the natural logarithm of n, as n approaches infinity, this will get bigger and bigger. And if you take the limit of this as n approaches infinity, it will get bigger and bigger. But then, when you do the division, you will see that this will take a finite number. So which means it's advisable to use a rule of limits called L'Hopital. I think there is something here. L'Hopital's rule. This method, L'Hopital's rule, will apply it here. So now what that means, if you take this limit as n tends to infinity, if you differentiate the ln of n, natural logarithm of n, you find the differential. Let's do it here. Let's say f of ln of n, and you differentiate this n. Yeah, when you see this apostrophe, it means we are differentiating. So this will give you now the limit as n tends to infinity. If you differentiate the ln of n, you get 1 all over n. If you differentiate n, you get 1. So all boils down to 1, the limit as n tends to infinity, you get any number divided by 1 is just the number itself, 1 all over n. So if n gets bigger and bigger and bigger, what do you get here? It's 1 divided by a bigger number. So you get 0. You get 0. So since you get 0 here, it means this equation holds. Then it means f of n, since this is 0 according to the rule, yeah, you get f of n is in big O g of n. Suppose you do it the reverse way. Let's say this is now solved here. Suppose it was like this. Instead of it was like this. Now g prime of n, f prime of this. Then what would you get? You see, suppose it was like this. If you differentiate n, f of n or g of n, you get 1. The limit as n tends to infinity. This one here, you get 1. And if you differentiate the ln of this, I was writing the ln of n. What do you get? You get 1 all over n. So you have 1 divided by 1 over n. What does that mean? So it's the limit n tends to infinity is 1 all over n. Yes, 1 divided by 1 over n. So you get n. You get n. So what happens when this n goes to infinity? When it keeps getting bigger and bigger and bigger, what happens here? This n2, it will get bigger and bigger and bigger. It will go to infinity. So if that be the case, then big O g of n is not in f of n. See now? So the reverse is not true. Go this way, f of n is in big OG of n. So now when we change the functions, now this becomes the other one becomes the other one. Now it's not possible because we're getting infinity. Before we got a finite number, yeah? Now we got 0 before we got 0. Now we got infinities, big number. We don't know what the number is. Infinity, we don't know. It's just a big number. So then g of n is not f of n. So we'll stop here. Thank you for watching.